All right, we can go ahead and get started. Today we have Sophie Goliber here. She's going to be doing her PhD talk. A little bit of an intro. Sophie got her bachelor's degree in geology from the University at Buffalo in New York. She's been working on her PhD for the past few years with Ginny Catania, focusing on glacial termini in Greenland. Sophie's been, a familiar face here at UTIG, doing a lot of outreach, DEI work like that, and it's been great to have her around. I've learned she's going to be doing a postdoc back at the University at Buffalo when she finishes her PhD. Today is a PhD talk, so I'm going to be putting the form to fill out so she can be considered for Best PhD Talk in the chat, and I'll probably post it a few times in case more people show up. But take it away, Sophie.
Thank you, Erin. Okay. Already said my screen is shared and hopefully everyone can hear me. And I can't see anyone's faces, so either unmute or I guess chat, I might be able to see if anything happens. You need to get my attention. So the title of my thesis is Controls on Terminus Change of Marine Terminating Glaciers in Greenland over the last 40+ years. And of course, like everyone's thesis title, quite a lofty title. But I'm actually just going to be focusing on 2 chapters today. One is a database of terminus data that I actually presented on the fall. So if you went to that talk, it's probably going to be a lot of repeat from that with a couple new things. But if you haven't heard it, that's also recorded and you can find the longer version there. And then the second chapter is looking at geometry of Greenland beds where glacier termini are stable. So it looks like a lot of people here are familiar with glaciers from what I can tell, so I won't spend too long on like the intro part. But I started this talk with this image that I start most of my talks with of Kangerlussuaq in West Greenland, which I definitely butchered the name of. But I think it really exemplifies the complexity of these glaciers in Greenland. We have plumes coming up from the surface that are buoyantly rising and melting front. We have icebergs that are calving off, really variable topography, and shows that the terminus is, an extremely complex environment, and we need all the data we can get to understand it and analyze that data. But apart from glaciers just being cool and pretty, they're massively important for understanding sea level rise. And Greenland has been shown to be losing about 286 gigatons per year of mass since 2010, and that's a lot. Sounds like a lot, but a gigaton isn't exactly intuitive. So here's a graphic, which I'm not sure if the video is working for you guys, but this visualization up top is what 1 gigaton of ice looks like on Central Park in New York City, which is a very large park. So as Greenland holds potential to raise sea levels by 7.2 meters if it lost all of its ice, and it has contributed about 6.85 millimeters of sea level rise since 2011. There's a very large range in the sea level rise contribution between 5 to 33 centimeters by 2100. So we need to get a little bit better estimates, so we need to understand what's happening in these ice sheets a little bit better. Next slide. Okay. So we know that Greenland is in overall negative mass balance. So we can look at those components here. Shown blue is our surface mass balance. Our melt is and red is our dynamic contribution. Purple is the combination of these two. For Greenland, this dynamic loss is dominated by outlet glaciers. So these marine terminating glaciers that drain the interior ice rapidly into the ocean. But there's significant heterogeneity in how these glaciers are changing. So this figure on the right is just showing from 2000 to 2010. There's a lot of differences in the amount of terminus change. Some are retreating, some are advancing, some are retreating a lot. And then this figure on the right is the velocities around the ice sheet, which are very different for different glaciers, but mainly what I wanted to get out of that is that there's over 200 named glaciers here, and even more that don't have names. So there's a lot of these features that are draining the ice sheet. And a large reason that the response is so different is what I showed in the beginning. That the terminus region is the complex interaction of the ice, ocean, atmosphere, and bed topography. This figure, is a little bit more complex version of that picture that I showed. And we see a number of processes that are interacting at the front, which makes them a very, dynamic and interesting part of the ice sheet to study and understand. There's been a great deal of research focused on quantifying outlet glacier changes and understanding how ice-ocean and understanding ice-ocean processes, and looking at how these many glaciers I showed change over time allows us to link observations to processes that are acting on these glaciers and how that's going to change future mass loss. So in more detail, I'll go over how the terminus changes from these awesome graphics that Jenny has created. So for one, as the termini, the front of the glacier reaches flotation, it produces basal crevasses that can propagate upward, interacting with surface crevasses, and that can produce calved icebergs with the position of the terminus stepping back from where those crevasses were propagated. We also have warm, salty water that enters the fjord at depth, and that can melt the front of the glacier, causing it to step back. Surface melt also occurs at the top of the ice sheet or the glacier and makes its way to the base and conduits known as moulins. Here's a really cool picture of one of those where we have this surface melt entering the glacier. And it emerges from the base of the glacier where it can drive a turbulent meltwater plume. And that's entraining this warm ocean water at depth, causing it to rise across the terminus face. And this can cause undercutting that sloughs off icebergs. So this is that same glacier that I showed in the beginning. You can actually see where this plume has breached the surface, and there's an indentation where the terminus has been changing due to undercutting. So there's a number of processes that are influencing glacier termini, and these calving styles depend on glacier geometry and environmental forcings. However, as the glacier retreats or advances and its geometry changes or how the environment changes, the dominant style of calving can change over time. And although high resolution models have been developed that are capable of producing these different calving styles, there aren't really any calving laws that accurately describe how all glaciers lose mass or how these change over time. I'm sorry, my cat is screaming outside, so I'm sorry if you could hear that. He's not a fan of glaciers. So in my first chapter, we're really looking at how we map these termini. So terminus change, mapped from satellite and aerial imagery, is how we actually understand how the outlet glaciers are changing. And they're sort of the poster child for climate change. You see it on the internet all the time. And these traces are mapped from satellite imagery. So this picture on the left is actually something that I did for an HU poster back in 2016. And here I am years later still looking at termini. And as Erin mentioned, I'll actually be going back to Buffalo to look at termini again. So I'm going full circle. So on long timescales, we can use terminus records to inform timing, regional pattern, climate control, and climate controls on retreat. So on this figure on the left, King showed that the increase in glacier discharge in the early 2000s was due almost entirely to the retreat of the glacier front. And in 2021, this paper would use an ocean thermal model and terminus position showing that glacier retreat was most likely triggered by ocean warming. But we also have this increase in retreat, even though there's a cooling. So there's something else going on in the terminus that we will get into a little bit later in my second chapter. So even though there is increasing discharge and retreat, there's also significant heterogeneity in the amount and duration of terminus retreat across the ice sheet in response to these climate forcings. So between 2001 and 2010, across the ice sheet, there's a lot of different changes, which, there's different ocean temperatures across the ice sheet, different atmospheric forcings. However, even when we zoom into an area with a smaller geographic region where regions are experiencing similar environmental forcing, we can still see this heterogeneity. So we have our retreat onset here, and then glaciers are retreating at many different magnitudes and for different durations. On shorter timescales or seasonal timescales, from months to years, we can get a better understanding of environmental and glaciological processes that are influencing individual glaciers using these terminus records. So Mason Freed, who's a previous PhD student at UTIG, with Ginny, showed there's these two types of calving styles in Western Greenland, sort of like what I talked about earlier. We have this buoyant uplift from basal crevasses meeting each other, creating this full thickness separation, which causes a step back across the entire terminus, so equivalent across all of these boxes, versus on the right here with the meltwater plumes causing undercutting, driving terminus change at a greater rate in this single area. So I'll get into my first chapter here, which is actually collecting a database of manually traced Greenland specific glacier termini. So all of these studies listed in this plot here are studies that have used glacier termini to say something about what the Greenland ice sheet is doing. However, a lack of coordination across these studies results in duplicated data, heterogeneity in terms of format, quantity, method, location, temporal coverage, availability, and it's a very laborious process to actually map termini. So here's a little video of me mapping this terminus, and there's upwards of 500 or more images per glacier, and the data set from Ginny Catania's work in 2018 used the entire Landsat record to pick 15 glaciers in central West Greenland, and she estimates that it took 3 undergraduate research, 2 summers working 15 hours a week to download imagery, pick the full width of the terminus, or about 48 hours per glacier. So all of these factors can limit the utility of this terminus data to researchers, even though it's very important to understand how these glaciers are changing. And with the Landsat archive alone, there are 8 satellites that have been collecting data since 1972. 2 are currently collecting data. Landsat 9 just launched. There's all of these other satellites that we can get data from. And we are going to be having data for a long time. So one sort of outcome of this is the use of machine learning techniques for automated picking. And this, can reduce time-intensive hand-picking of termini for future and missing data. So a collaborator on the TermPix paper, Daniel Chang at UC Irvine, developed CalFam, which uses these neural networks to automatically detect glacier termini. His data set uses has about 22,000 calving front lines for 66 Greenland glaciers. However, the machine is not perfect. There's a need for more training data for this to be a little bit more successful in times of heavy ice in the launch, glacier trunk spitting, other poor image qualities, or we'll need more data where the machine just can't pick the data, so we'll need hand picks for those regions. So TermPix is actually a collection of all of these 22 original sources from 18 different authors. This is probably not a complete set of all terminus traces that exist in the universe, because we're just focusing Greenland, and a lot of the data had to be requested via email when it wasn't available in any sort of data repository. So, they're coming from a large range of places around Greenland, date ranges, resolutions, methods of picking, and from a lot of different image sources, although a majority are coming from Landsat. So in my last talk, I spent a lot more time focusing on the quality of data and like how we homogenize it, but there's a whole hour talk about that, which you can find, I think, on the UTIG archives, or you can watch my AGU talk. So quickly, I'll just say that this workflow is homogenizing the date formatting, satellite image source, the original author of the trace. We use quality flagging to identify where traces may have sources of error. And this flagging scheme was also created in conjunction with the Calvin data set, so you can use term picks alongside the machine learning data. And very importantly, we also use Google Cloud services to assign Landsat data to picks so that they are associated with the original image, which is important for machine learning. So after doing that process for all of our glaciers, we have our 39,000 individual traces for our 278 glaciers. Again, I'm not going to spend too much time on this. Here we have author error, which obviously is going to be very varied between different authors. We use the Hausdorff distance as a metric of error, which is used in pattern recognition. It's the greatest minimum distance between two lines. And we have about 2,600 individual traces where multiple authors picked glaciers on the same date using the same sensor, so we can actually get an estimate of inter-author error. And it's around 107 meters, which is comparable to machine learning studies when they're comparing machine traced termini to manually traced termini. And also, you can see that there are some very massive errors between authors, but this doesn't necessarily indicate inaccurate digitization by authors. And for very large ones, we actually went and manually checked a few of them, well, a lot of them. But for example, this large error between like Hill and Chang and ESA data sets are because these authors were focusing on northern glaciers, and these northern glaciers have very large floating tongues that have large crevasses, and so the detail you pick a glacier termini may affect this error estimate that we have. The bulk of our traces are from 1990 and onward, which is very much linked to Landsat acquisition, which is here in these blue arrows. So we have much more data after 1999. We have Landsat 7 and Landsat 8. And we also have just fewer traces in Southwest Greenland, as you can see here, because there's just fewer marine terminating glaciers. The densest coverage we have is going to be in northwest and south, central west and southeast. Because of that, there's a large number of marine terminating glaciers in these regions, but also central west and northwest were where Ginny worked. So there's 15 glaciers there that have, the most complete record of this whole data set. And other large glaciers of interest include Helheim and Jakobsgraben in these two in central west and southeast. And they also have very dense coverage, so they're going to drive these numbers up. So this data set is allowing us to have a longer, more complete time series view of glacier change. So each of these plots on the right is showing how many years each glacier can resolve a seasonal signal. So it has more than 3 picks per year in 3 unique months. And so this isn't even including glaciers that cannot resolve individual picks. Cannot resolve seasonal signals. So these are only authors that have more than 3 per year. So term picks, because it combines all of them, is able to do the most. And the example plots over here on the right for glaciers 116, 109, and 185, this red line is our retreat, and the colored lines, the dots, are seasonality. So purple is going to be term picks, and then the orange is going to be an individual author that can resolve seasonality. And so for all of these, we can see when you combine authors, including authors that don't resolve seasonality on their own, but when combined with others that picked glaciers at different times during the year, we can actually resolve seasonality. So for example, Glacier 85, no single author had enough picks to get seasonality, but when you combine them, we actually can look at it. So they're all indicating that these seasonal swings, so we have upswings in seasonality in the terminus vision, could be amplified during these periods of retreat. So we wouldn't be able to examine this without these clean data sets. Another example of why it's important to have the full terminus and map view rather than just an individual point along the center line of the glacier is looking at the sinuosity. So in orange, now we have our retreat for these two glaciers. And the bottom is the corresponding terminus change for both of them. And in blue is the sinuosity. So for Glacier 288, we can see an increase in sinuosity at the onset of retreat and overall decrease during the rest of the retreat. And Glacier 291 has a relatively high sinuosity, but doesn't really retreat for the entire record. So these changes in sinuosity may be correlated to these changes in retreat type that I showed earlier. So Mason looked at this, but by obtaining the full map view of the terminus rather than just the center line, we can actually examine changes of the shape of the terminus over time. And I'll go into this more in chapter 3. So if you're interested in that, you're going to have to come to my defense. So that's all I'll talk about for term picks. As I said, that's been presented and recorded. So I'm going to spend some time on chapter 2 now, where I'm looking at the geometry of stability points in Greenland glaciers. I haven't talked this much in forever. My goodness. Okay, so bed topography has major impacts on the stability of glaciers. And a large factor in this is that as a glacier retreats into a retrograde slope and becomes thicker, the flux has to increase, creating a feedback loop. You know, as that glacier retreats into deeper topography, it will create this loop, also known as marine ice shelf instability. So that implies that these places where the bed topography forms a moraine or a lateral fjord restriction can be pinning or stabilization points for glaciers. As the ice flux decreases, the glacier becomes restricted. As the glacier becomes restricted, excuse me. And detachment from them can cause accelerated retreat through these open deepenings. Additionally, steeper prograde slopes of glaciers can actually reduce upstream thinning, which increases stability and decreases retreat. And we know glaciers react to mass loss and climate changes very differently depending on their bed topography. So here we have two glaciers in Western Greenland, and these glaciers are both experiencing similar climate variations, but the retreat response is very different. Excuse me. We have our termini here in map view, and then along the slide up here showing a time where that glacier is located. And we have stability at positive bed features. So for Umi here at this peak, Store Glacier here, there's a lot of variation. So this is the mean bed and this is the minimum bed, because this study that Jenny has done is focusing on the mean bed across the fjord. So we wanted to take a look at sort of the lateral variation and see if these differences in these positive bed features are making Umi retreat, but not Store retreat. Oh, my mouse is not showing the screen. I might be on the wrong screen.
I can see it now, but
Oh.
I couldn't see what you were pointing to in the last one.
Oh, okay. I was pointing at where I also have error. But yeah, so for this, the second chapter, the big motivating question is there a difference in the topography of an actively retreating glacier and that of a stable glacier? So we know several studies have shown the importance of bed topography, but we haven't really explored the 3D geometry of positive topographic features that are present at the terminus of glaciers in Greenland when they're stable. So we expect that glaciers that are stable through our time series are grounded on their prograde side, probably have a higher bed peak and higher prograde and retrograde slopes, in contrast to retreating glaciers that might have that might start on their prograde side before retreating onto their retrograde side, might have lower bed peaks and lower prograde and lower retrograde slopes. So to start, we identify our glaciers as retreating versus stable using the Turnpix data set. We calculate retreat over the time series, and we also combine it with the Calfin data set to have a much, robust record of time. So we have retreat here. This is in map view showing the time. I forgot scale bars, but the color is indicating time. So if it's darker purple, it's earlier. If it's yellow, it's later. Sorry about that. And then we also locate times of stability using the same retreat timing. So if it's blue, that means the glacier does not have progressive onset of retreat, meaning that the previous summer to a retreat event is less retreat than it is in the summer. So we have this glacier here. Glacier 2 is relatively stable through this time. And then the progressive summer retreat is greater than the retreat in these years. And then it restabilizes, whereas Glacier 229 is actually advancing. However, glacier stability in the short term may actually be transient in the long term. So on the right, this is a modeling study where we have different retrograde bed slopes, and the glacier gets perturbed by some climate event in these four scenarios. And the persistence of that glacier on these bed peaks is very different depending on the retrograde slope. But in these middle cases, they end up retreating, but just at a time later than the climate perturbation because the glacier continues to thin. On the right, glaciers here have a greater likelihood to retreat when compared to on the right, glaciers show that the initial position, so here, the closer the glacier is, the bed peak, when perturbed, is actually going to determine the likelihood for it to retreat with or without climate forcing. So I'm calling these glaciers retreating or stable, but I'm not implying that they are stable and remain so, because eventually they may retreat. We're not looking at thinning in this study. But what I'm hoping to do is actually characterize the glacier configurations using these observations to see if there's correlations that have remained stable or retreated during this most recent warming trend. So just as an aside. To characterize the actual bed geometry at these stable positions that I've identified from the terminus record, we're using Bed Machine. So Bed Machine is a bed map for Greenland that's combining bathymetric radar surveys and a mass conservation approach, and it creates a seamless ice thickness and bed topography estimate in Greenland. And so this map uses data to constrain it, but we want to make sure that our regions, our glaciers that we're looking at, actually have good bed data. So this is an example of a map of a glacier. So green is a terminus position and gray is bedrock, excuse me. Purple is actually the location of bathymetry surveys, and red is radar. And so we can see the glaciers retreated, and this bathymetry survey actually covers the entirety of the fjord. So we know that there's good bed data here. In our next example, we have not as good data. So the multi-beam doesn't cover the entire terminus, but we do have radar. So we know that it's going to aid in the mass conservation calculations to actually produce this map. And then there's a glacier here with virtually no data. So glaciers like this, we don't actually use in this estimate. So after identifying where we have good or pretty good bed data, we then go back to where we have our estimates of retreat and where the estimates of these glaciers are stable. So Here, these blue colors are correlated to these blue colors on our terminus. Blue here is the ice flow direction, so glaciers up here, and this is where it's retreated from. So we know the glacier was stable for a time in this area. So what we do is look at what the bed topography looks like if we find a positive bed feature in that area. So for Glacier 2, there's this feature that we define as a bench. In the across profile, it creates this bench feature. Looks like you can almost sit on it, and a crest in the along flow profile. Also here, in the area where the terminus is not grounded on the high part of the bench, there's actually a lot of movement in the terminus, but it doesn't fully retreat where it's stable. There's movement. In our stable case, which I showed before, this glacier is actually advancing. It's advancing up this feature, which is a moraine, which is characterized by this crest on the along flow feature. Oh, also, sorry, I did not mention this. These green bumps are the apex, so this is the highest point of these bed features. And this is where we measure the bed peak and the slope of both the retrograde and the prograde side of these bumps in the along ice flow direction. Finally, we have this example of a ridge feature. So this glacier is stable near this positive bed feature, which has a W shape in the across profile and a crest in the along flow. So ridges are really the most complex shape that we see in these fjords. And there's a lot of heterogeneity in the bed here, but we attempt to pick the most prominent feature where we can see the terminus is very clearly located. We can also see there's a lot of movement around this feature as well. There's a swinging door, which I'll get into a little bit later around the feature. So we do this for 42 glaciers of interest in Greenland that we have bed data for. So it's a very small subset. These are the glaciers that we are more confident have good bed data. We identify 33 glaciers with at least one large retreat event and 9 stable glaciers. So obviously you can see this retreat population. You don't have to read all these numbers, but I'm showing that the retreat population is much larger than the stable population because more glaciers have retreated, but they also have better data, but I'll get into this a little bit more later. Excuse me. So a little bit of confusing vocab that I'll start to be using is that stable glaciers have features that we're calling stabilizing features, whereas retreat glaciers have features, positive bed features, we're calling transiently stabilizing features. So there's a lot of stabilizing being used, but I'm trying to keep this as clear as possible when I'm talking. Also to note that most glaciers are located in the northwest, central west, and the southeast, because that's where we have data mostly available for these regions. So first we have our transiently stabilizing features. So these are features that are present at retreating glaciers. So glaciers that were stable for a time and then retreated. 30 of these glaciers have features. 3 of them have no evidence of a stabilizing feature. 14 of these features are moraines, 8 are ridges, and 5 are benches. And the remaining 3, like I said, don't have any feature. The largest population is the moraines. Our bench features are covering about a width of 53 to 68%. So they're going approximately halfway across the fjord, whereas the ridges are covering about 27 to 53. So they're covering a much smaller range of the fjord. And as I said earlier, the ridges are very varied, and this could be because that 6 of the 8 ridge features are located within fjords, whereas there's a convergence of 2 glaciers upstream of the ridge. So that may control the location of ridge features. Also, our ridge features and our moraines have very similar prograde slopes. That should say ridges and benches have a similar prograde slope at 7.9 and 8.1, and the moraines are a little bit lower than that in this population. Oh, geez. For our stable glaciers, all 9 have a stabilizing feature where the glacier is stable. All of the glaciers except for one are moraine features, and the single feature that is a bench is covering about 66% of the fjord, so it's almost going across the entire width of the fjord. And where the bench ends is slightly raised, so it's similar to a moraine, but the majority of the feature is a bench. The slope of the bench is about 16 degrees, and the moraines have a mean of about 10. So they are in general higher than our transiently stable features. And so as I mentioned before, the population of stable glaciers was much smaller than the retreating glaciers. So to try to remedy this slightly, we look at places where retreat glaciers restabilize. So in this image, we have Glacier 2 here. It was stable here. So this is our transiently stabilizing feature. It retreated and then restabilized on this feature here. Of the 33 retreating glaciers, we identified 8 glaciers that had partial bathymetry or radar data. So we're able to identify our feature there. And these features are further into the fjord, so the bathymetry quantity and quality isn't ideal. So they're a little bit more difficult to discern a larger number of them. But 2 of the 8 are benches, and they have a very similar slope distribution to our stabilizing features. Now to compare our transiently stable to our stabilizing groups, we have a clear distinction between types here. So our retreat glaciers are made up of these ridges, benches, moraines, while only the stable and restabilizing glaciers are mainly moraines and benches. So the greatest difference between these populations is the prograde slope. So the transiently stabilizing features are around 6, whereas our stabilizing features are at 10 and 11. Particularly the moraines have a very large difference as well. So the moraines in the transiently stabilizing population are around 4.9 versus 10 for our stable populations. Similarly, the retrograde slopes of our stabilizing features is slightly higher, but because the stable glaciers are stable, there's no open ocean where the glacier is stable. The retrograde slopes are much more difficult to survey. So this is a slightly more difficult population to measure. The stable features are on average only about 85 meters thicker and about 55 meters higher. So the peak of these features is slightly higher. And our restabilizing features are often can be above sea level. So some of these glaciers are starting to retreat back to being above sea level. And finally, the percent of the fjord that it crosses is indicative of how much lateral variation there is. And so our transiently stabilizing features have a large number of moraines, but they also have a large number of glaciers that do not cover the width of the fjord, whereas our stabilizing features cover the width of the fjord, so they may be protected against intrusion of warmer ocean waters. To assess whether our glaciers were floating or grounded pre-retreat, we actually calculate the height of a buoyancy from aero DEM. So these DEMs are created from ortho photos that were taken over Greenland. So because they were done, by flying airplanes, excuse me, they don't cover the same regions the entire year, but they all cover times before that our glaciers went into retreat. So we want to see if our glaciers were floating or grounded pre-retreat to see if that impacts the stability of these glaciers. We use a 50-meter height of a buoyancy threshold for our near buoyancy following Van der Veen 1996. So in our 1985-1987 time range, our stable glaciers are about 35%. They have a higher median height of a buoyancy, so they're more grounded when we compare to retreat glaciers. And retreating glaciers are also mostly grounded, but around 19% of them are near floating. So our population is slightly less grounded than we have for our stable glaciers. To assess what side of our features our glaciers are stable on, I interpolate 150-meter points along each terminus and sample if the glacier is on the prograde or the retrograde side of the bed, or if it's not on the feature at all. So while some features are on, bumps or ridges that don't cover the entire width, I'm scaling the percent retrograde and percent prograde to be only for the feature itself. So for each of these plots, the top is going to be the centroid distance of a terminus to the apex of the feature. And then the bottom is, for that terminus, is it prograde or retrograde side of our feature? So if it's purple, that means part of the terminus is on the prograde side and the other side is on the retrograde side. So we have these 5 modes of retreat that I've identified for glaciers. Modes 1 through 3 are applicable to retreating glaciers, and the other 2 are for stable glaciers. So this glacier, Glacier 3, starts on the prograde side of a feature, and then when the onset of retreat occurs, it retreats over the feature and onto the retrograde, and then finally off of the feature. Mode 2 we see starts on the retrograde side, which is red, and then continues retreating. So it's stable for a time on its retrograde side of the bed, and then it retreats. And some glaciers, such as Glacier 2, actually oscillate over the feature. So it's purple here, meaning part of the terminus is on the prograde and part of it is on the retrograde. So it's not on either side dominantly before it retreats. Stable glaciers either remain entirely on the prograde side, which we see here, or they oscillate but do not retreat. So they remain sort of at the peak of the bump, but they don't have any sort of onset of retreat. So here we have our retreat glacier modes located by the retreating glaciers and stable glaciers. So 11 retreating glaciers present in mode 1. So that's the prograde to retrograde, sort of what you expect. 9 are stable in their retrograde side of the bed before they retreat, and then the remainder are oscillating. Excuse me. And in these stable glacier modes, a majority of them remain on their prograde side, but about 44% of them are oscillating. And all but one glacier of the stable glacier population have an average terminus position of being prograde for the entire record. So only one stable glacier is actually stable on its retrograde side. Finally, listed here on the left side here, retreat glaciers with transiently stabilizing features have a mean distance of about 1.2 kilometers away from the bed peak before the onset of their retreat, whereas stable glaciers have a mean distance of about 1 kilometer. These are driven up really highly by this glacier here, Glacier 33, which is a very large stabilizing moraine, which is much different than the rest of this population. So removing that, the standard deviation gets a little closer to about 0.5 kilometer. So the stable glaciers are often much more closer to the peak of their bump for the entirety of the terminus record. So they're not much further ahead of the prograde slope, they're much closer to the peak. So from this analysis, we can see that glaciers may be intermittently stable on their retrograde bed feature, but all of these glaciers retreat after being stable for a short period of time here. So none of them are stable for a very, very long time here, which makes sense. Glaciers that retreat onto a retrograde bed should retreat as the glacier thickens and we're increasing ice flux. Glacier 264 is the only glacier that is located on the retro side of a stabilizing feature and remains stable. However, the terminus is advancing, so the glacier is pushing forward, and the fjord is actually narrowing just before the presence of this feature. So that might be causing a confluence of ice there, even though it's on the retrograde side. And finally, the more the closer a glacier is to a bed peak, the more likely it is to retreat with or without a climate perturbation. So these glaciers are very close to their bed peaks. And the position that the glaciers are in now does not preclude them from retreating, given this forcing that has happened or forcing that will happen in the future. As most stabilizing features are moraines, and those stabilizing features have much higher prograde slopes than transiently stabilizing moraines, this may be a very stable feature for Greenland glaciers. It may be that these glaciers are actually building a moraine, and therefore the prograde slope is increasing. And as these glaciers are funneling through a small opening at the top of their moraine that they're building, you know, the ice flux is increasing and it's maintaining the glacier just after the peak of the bump. And if the glacier is on a high enough peak, it may actually be out of a warming ocean enough not to be affected by climate forcing that's happening. However, as I mentioned before, we're looking at a very small time period, and there may be longer term cycles, and we're only capturing a very small portion of them during this time series. So for example, in Alaska, the Tidewater glacier cycle, which is shown on the right here in this GIF, is where glaciers actually build up a moraine, they remain stable on it, but the glacier cannot, retain a sufficient enough thickness to remain on that bump, and then it retreats and the cycle starts again. And this is happening irrespective of climate. But as climate warming increases, these stable glaciers in Greenland may thin, and so they may not be able to remain stabilized on these bed peaks, and then they may retreat off of the moraines, in a similar fashion to what we're seeing in this feature. Sorry. Finally, we also notice a trend in retreat styles in different big bed configurations. So here we're defining this swinging door retreat as a style of retreat where part of the terminus on a single date is greater in one place than in another. So we can see that here where we have sort of differences in the morphology of the terminus laterally. Out of all of our glaciers, 23 of these glaciers show some evidence of swinging door retreat just after the bed peak. And 22 of our 33 retreat glaciers show this. All retreating glaciers that have a bench or a ridge show this swinging door retreat. So the feature itself may be controlling, the morphology of the terminus. Only one stable glacier has evidence of swinging door retreat, and this is Glacier 284, which is the one that has a bench. So it has an actual deeper part where the swinging door retreat is happening. So these bed configurations may be giving rise to these different retreat styles across the terminus. So this may complicate how calving occurs and how it's actually treated in models. So on the right here is Humboldt Glacier in northern Greenland, where one part of the bed is very deep and one part is very shallow. And so we actually see differences in morphology across the front. And in a model done of the north and south transects, the glaciers are affected very differently by crevasse water depth and sea ice buttressing based on the different portions of these glaciers, where the bed was more deeper and more shallow. So this glacier is about 45 kilometers across, which is 40 kilometers greater than average in Greenland. So it might matter a lot more here, but currently calving models only use a single law over the entire front and over entire time series. And none of them do a very good job for all glaciers shed. So as the calving style may change over time, we need better parameterizations, and this might be based on these lateral and along flow differences in bed topography that we're seeing. So this study's limitations, there's any for any study, but there are a few for this one because we're looking at a very short time period for a very small number of stable glaciers. So we may be only capturing a time of transient stability in a very much longer time record. The bed is also very coarse, and so small scale variations may be smoothed or missed. And so some future directions based on this work are looking at where some of these glaciers actually have other positive bed features that the glacier retreats over. So why does the glacier ignore them? And can we actually use the shape of the terminus, as I mentioned in the last slides, as a proxy for processes that are acting upon the glacier? We use these differences that we're seeing to better parameterize how glaciers are having. And as stable glaciers may only be transiently stable, can we sort of make inferences on if they're going to retreat in the future? So are the glaciers thinning? If they're continuing to thin, then we might be able to expect them to retreat at a later date. Also, how are these glaciers that are stable building their moraines? This will give us a lot more insight into why they're stable. And Ginny just got a KEC proposal funded, which is going to Western Greenland to hopefully answer some of these questions. So I have some conclusions. I don't know what time it is. So 53. Okay. I'll be talking a little bit more about lateral variations and terminus morphology in chapter 3. So if you're interested in that, come to my defense on July 7th to learn more. But that's all I have now. Oh, my throat really hurts. So thank you so much for coming to my talk. It's been a really rough couple of years for everyone, I'm sure. So this is my favorite poster of the Hang in There cat. And these are my cute office mates that make everyone smile. So I thought I'd include them at the end of my slide. And I'm going to end slideshow so I can see everyone's faces.
Awesome. Thanks, Sophie. If anyone has any questions, feel free to just unmute yourself and ask, or you can post them in the chat and I can read them out.
Hey, Sophie, this is Duncan, if you can hear me.
Yep.
Great stuff, tremendous amount of work, and quite impressive. I guess, let's see, Landsat, it's optical, you've got seasonal restrictions on when you can image stuff, and also cloud restrictions. When you compare that to, say, the term pics includes pics from SAR or not? Have you done a comparison between those two methods, and is there any sense of things that you might be missing with the optical that you do get with the SAR, or vice versa?
Yeah, that's a good question. And I actually haven't looked at the differences between the satellite types. In general, there's just a greater amount of data in after 2005, 2010, because we have Sentinel. However, because you don't have, the cloud cover issues, and you get better visibility in times where optical has not very good visibility, then my guess would be that you're getting a lot more seasonal signal. And actually, one thing that I didn't show in that figure is I'm just showing the number of years that resolve seasonality. But the actual time periods that resolve seasonality are much later. So late 2000s. So off the top of my head, yes, there's probably going to be a difference in the time that you're getting from SAR versus optical, but just having SAR is so much better than just having optical. Having SAR included in the optical is so much better because you're missing a lot with Landsat, especially in the winter. and the melt.
Thanks.
Got time for another quick question?
Thank you, Natalie.
All right then. Thanks again, Sophie. Good luck with your dissertation this summer. You're definitely going to kill it. And good luck with your postdoc.
Thank you. Thanks everyone for coming.